Here we go. Now everyone else can have class too. But these are how the rates relate to each other. Remember, you're going to have the fractions of the coefficients from the equation. This is how they relate to each other. If you're just talking about the rate of a specific compound in the reaction, that's going to be your change over time. All right, so if we look here, now we're back to our ammonia equation. And so again, you can see the graph where you have the consumption of the ammonia, the appearance of the hydrogen and the nitrogen. You now have a way to see why the nitrogen appears at a much faster rate than the nitrogen. But we need to talk also about instantaneous rate. So instantaneous rate is, essentially that's going to be a derivative of one of the curves. And so your instantaneous rate is going to be the rate at a single individual point. So that's what a derivative is. It's infinite decimal. So you have a change in time that's infinitely small. So it breaks down to a single point on the graph. And so then your derivative is going to be a tangent to that curve. Your rate is going to be the slope of that tangent. It is. Granted, you don't have to reproduce calculus in any of your exams or homework, but we are going to do it because one thing I don't like about textbooks is for some classes, they have to make asinine assumptions just to get you to the theory. I'd rather just start from first principles and show you where it comes from. Now, whether you learn the calculus or not, that's on you, because again, it's not going to be something you're tested on. But I will show you where things come from. Because as I said, we have to start thinking beyond what we're comfortable with. By the time you're all through graduate school, you're going to be doing a lot of this stuff. You're going to have to, like, well, where does this come from? How do I figure it out? I need to start from first principles. How do I get there? All righty. So here, let's say we have the thiosulfate ion. It's oxidized in the following chemical equation. Let's see. In an experiment, 7.5 times 10 to the negative third moles per liter of thiosulfate is consumed in the first 11 seconds of the reaction. Determine the rate of production for S4O6 for that first 11 seconds. So here's something here, like some vocabulary to keep in mind as you're going through more advanced classes. That prefix thio is always going to mean some kind of sulfur group. Okay. Not sure why thio got equated with sulfur, but somewhere along the line it did. Been that way for centuries. All right, so how do we go about this? So we need to relate the thiosulfate to the S4O6. So we look, well, we see there's a 2 there. Technically, there's a 1 there. Okay. So that means I can say -1/2. Now that's tiny, but it's a -2. Now, of course, you see the thiosulfate is negative. The S4O6 is positive because the thiosulfate is a reactant. The S4O6 is a product. Again, your reactants are going to have negative signs. Your products are going to be positive. Okay, so now the rate of consumption of the thiosulfate going to be the rate of change over time. That is going to be, oh, hang on, what was I looking for? Oh, the rate of production. Let's reverse this for a second. Let me put this one in here. So then I'm going to take that 1/2. And my rate of change, so the change in thiosulfate over change in time, that is going to be, so when delta T is 11 seconds. When I calculate this, I'm going to get 3.21. So that's technically molarity per second. So that's concentration per second. So, but you use these rate expressions to relate the consumption of species to the production of species in a reaction. So look at some of the numbers I put in there. So why did I make that 7.05 negative? Right, it's being consumed. So that's why the extra negative is on the front there. That makes, so that'll make that whole thing positive, and that's going to make the appearance or the production of the S406 positive. You get that setup. Again, you're relating everything through this. So we say the thiosulfate has the 2 coefficient. This one has a 1. That's why I get the 1/2 here, and I get no fraction there. If I was to put a fraction there, it'd be 1/1. Uh-oh. Solve this one. I like this question because the ACS final does a lot of stuff like this to you. They don't give you a compound. They'll just give you compound A or X or. This one's a little harder. It is C. How'd you do that? Uh-huh. Yeah. So, I mean, you can start by saying, well, how do they relate? No, 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 absolutely not. No. You cannot make a phrase out of something that doesn't mean anything. TikTok is single-handedly destroying the world. Okay, so we can start by saying 1/7. And then on this side, 1/6, and then the appearance of the water. All right, well, Yeah, I would. I mean, because what you're really going to want to do. So we're just going to make that X because again, that rate takes the negative sign with it. Okay. And that leads you to answer C. People who didn't risk an answer, how'd you do? Do you even want to tell me? Yeah, that happens a lot with this until you get used to how they work. Well, so it tells you the rate of disappearance of oxygen is X. So I have to put that in there. What is the value of what is the uh, value of the appearance of water? So that means if it says that, I want to get that by itself. So I'm going to set it up to the proper relation. I know the negative sign goes into the X because that's the rate of disappearance. And so since I want to get the water equation by itself, then I have to multiply through by the 6 and get rid of the fraction in front of the change in water over change in time. But yes, until you get used to these rate expressions, you tend to you flip them upside down a lot and get them reversed. And it just takes some practice. Okay, rate laws. So we have a nice chemical reaction here. There's sodium chloride reacting with calcium carbonate. You get sodium carbonate and calcium chloride. What kind of reaction is this? Double replacement. It is also an equilibrium because that double arrow's there. Now, notice how I put that nice little K above the arrows. What is that? Rate constant. Yep. So our rate law, okay, so we've been talking about rates. Now we're talking about rate laws. Okay. Now, this in fact is what's known as a different. Come on. Well, that usually works. Don't die on me. Oh, there we go. When I was an undergrad, we still have the some people still have those cathode ray tube computer monitors, those big ones. My friend had one with he had it. He had an X on the side of his machine and it said smack here. And it worked. He would just waylay that monitor and turn back on. So this is what's known as a differential rate law. Did it turn off again? Okay, so now notice how these rate laws, we're really going to make them we're going to form them out of the reactants. You're going to get exponents in and in. Now, there will be a time when will be the coefficients in the reaction, but that's what we call pseudo first order. So yeah, pseudos they kind of like that are trying to be that, but really isn't. Where?
Yeah, what is that green light?
Oh, logic symbols. There's an entire alphabet of logic symbols in mathematics. The 3 lines means equivalent to, that means this is a definition. It means this absolutely equals what comes out. So K is your rate constant. N and M are the orders of each reactant. N plus M is going to be the overall order of the reaction. So imagine N was one and N was one. It would be, so the reaction would be first order in each reactant, second order overall. So a little more in depth than what we did in the lab. N and M are usually figured out experimentally. So we end up having to have data or have experiments we can perform that will allow us to figure that out. Now, I've abridged the equation a little bit. Now, I just used one because a lot of times these are in steps. You have the entire reaction mechanism. But you notice the difference between the rate constants. You're going to want to pay attention to that. The positive subscript is a forward reaction and negative subscript is a reverse reaction. So you're going to have rate constants going either way. And the way you change the way the rate law changes, you're still going to have concentrations of the reactants. It just depends on which rate constant you put in front. Is it the forward or reverse rate constant? Also, each order of reaction has its own units for its rate constant. So you're going to want to start getting used to that too. There's zero order, first order, and second order. Those are the ones you're going to worry about. All right, so if we look at this equation, what we can say is, well, our rate. Now I know this is going to, let's just compare it to sodium chloride. Well, let's do both of them. No, sodium chloride, I'll do this one and that one. Okay. This is going to be, okay, so if I'm comparing my rate law to sodium chloride, is it going to be K1 or K minus 1? Sodium chloride decays, and which way does the reaction go? K1. Because I have to go forward from here. This one, so if you're starting with a product, the rate of the product, you're going to go backwards. Okay. And so then we'll just call this rate prime. Now notice I still use the concentrations of the reactants. It's affected by the rate constant that I put in front of it. Now, we can also find ways to compare the rate constants to each other. Should I make you figure this out? No? Yeah. Oh, I didn't give myself enough room. Did I? Oh, no, I did. Okay. So let's say that take a few minutes, see if you can figure out why this is the case. Nope. So what this is saying is the forward rate happens at twice the reverse rate. Nope. Nope. I'm getting mixed looks of I don't know and I don't wanna. Yeah, can you prove this? So think of the question more instead of like a qualitative why, can you prove this? Always remember, I'm a physicist. How do I form arguments? Well, yeah, there you go. Kind of. What if we had, okay, so then that means, the point is be like dog. Don't be a jerk, just wobble gobble. So then let's say we leave that there. So the negative. Okay. Now I have definitions for those. A very straightforward proof. Mm-hmm. Yeah, so if we go back up, that negative 1/2, because there's a 2 in front of the sodium chloride. Yeah, and the rate of the sodium chloride's got to be negative because it's being consumed. So then you do 1 over that 2. You notice that the CaCl technically has a 1. And so it's not going to get a fraction in front of it. So you set up this equivalence, you multiply through by 2, and then you substitute each one of these because we have those right there. Because once so you start with the 1/2, you multiply both sides by 2. 2 times 1/2 gets rid of the fraction. And so then there's a 2 left on the other side. You just do the same thing to both sides. that is consumed into the rate. So see, your rate, your consumption of your reactant is always going to be negative, but then you get it equals the rate law. Did it? No, no, it did that. It did that because look at the rate law. I was worried about comparing a reactant to a product, the sodium chloride to calcium chloride. But the rate law is always going to be expressed by using the reactants. The difference in the two, do I use the forward rate constant or the reverse rate constant? So that's the difference between the two. So when I substituted, you see the calcium chloride here, I get the same rate constant I get the same rate just with a different rate constant. That we're trying to, like, you can start to understand things like that. You're doing an experiment in the lab, and you're trying to explain what you're noticing. Well, this tells you that the forward reaction is twice the negative, which is twice the reverse reaction. So that means you should be getting more forward reaction than reverse. Yeah. So your rate forward is going to be twice the rate. So that's why you do things like this. You make comparisons and trying to easily explain, compactly explain what you're noticing instead. Okay. Oh, here's a fun one. Let's see if we can solve this one. Well, I think I know our definitions of fun are different. Your definition of fun is not doing chemistry. My definition of fun is watching your faces go, oh man. I get some kind of sick joy out of it. Oh no, he loves this shirt. And I had to get this because in the past years, my students keep asking me biology questions. Like, I am a physicist, high energy physicist. I don't know biology. I was the one walking around my first year here going, I reject human, wish to return to monkey. And the students went, that's not how it works. I'm like, let me have this one. I don't know how it works. So, I think this makes the point very clear. Where if this was brush class, you could name all these different parts. For me, it's bird, 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 bird. I don't know what those are. So, huh? Oh, everyone knows that one. It's the mitochondria. That's a high school thing. No, not even close. Just don't tell us. I mean, I can even tell you that communication through different subunits of an enzyme is through salt bridges, but that's as far as I go. Yeah. I learned that one by accident because I had a professor in graduate school who thought physical chemistry was the same thing as biochemistry. And I was like, mm-mm. But, when he's in charge, he was also the professor who dressed like, who is the Apple? Steve Jobs. He always had like the black turtleneck on, and then he would write on the chalkboard, and then he would try to look like real thoughtful, and he'd lean against the chalkboard. He'd then turn around, he had perfect equations on his back. It was great. What is his name? Richard. I'm not telling you. Oh, Richard. Yes. I think so. So how do you think we solve this?
I got.
That is not even close. Did you just throw that out?
Actually, that.
Okay. I got 166. Oh, okay. Well, let's start by doing ratios of the rates. Okay. So if I did, yes. He's actually one of the most brilliant biochemists I've ever seen. He's able to explain to you what almost every electron in an enzyme does. Yeah. That's an old picture. He's in his 70s.
Jeez.
So if we do this, we're going to do the 0.012 over the 0.008 because I want to put the larger number on top. That'll give me easier ratios to work with. This gives me 1.5. What is 1.5 in fraction? 3/2. So now I'm going to multiply through. And let's get a fraction on each side. So what would I move to the other side? So if I want these to come out looking like our equivalencies, what would I move to the other side? Nope. I'm going to leave the 2 where it's at. And so I end up with 1/3. I like that answer. I think the answer is now 166. Like if you did that on an exam, I'd be like, well, that's the answer now. So we can do that. Let's and then let's say we need something to compare to the rate of C. So I don't know, let's do C versus A. Okay, so that's going to be 0.0160. This will give me a straight 2, but what is 2 in fraction form? Nope. Yeah, what's 2 in fraction form? It is 2/1. That's true. But that's not what we're going for. Yeah.
See, it wasn't the most correct answer.
You know that's how we do things in this school. What's the most correct answer?
See, that's right. It's not. It's
Which this will give me 1/2. Oh no, hang on. Not 1/2. I'm going to take the 4 over 1/4. Now, if you notice, the delta A over delta T gets 1/2 each time. The delta B over delta T gets 1/3. And the delta C over delta T gets 1/4. So what do you think A, B, and C are? So if we do A plus B plus C, with these as our results, what are the coefficients? Do what? Yeah. So, yeah, do A, you probably could. There's a different number of ways you could solve this. You just want to start making these comparisons and try to figure out what these coefficients are. You could also theoretically do 3 equations, 3 unknowns, make it a linear system.
Yeah, yes, yes.
Well, if that's how you guess, keep doing it.
Well, I just put them in order. I did 0.008
Uh-huh,
and then 0.012
uh-huh.
equals 0.016. I just sit.
It worked. Yeah, so yeah, I mean, that's another way you can do it.
So confident that
Okay, so kind of want to talk about this to let you know what we're going to be covering the next time we meet, which is when are we having class again? Monday. Because I'm at a conference on Friday. Don't celebrate too much or I'll put a video up on Canvas. I won't, but that's just. Yes, you will have a quiz show up on Canvas, make sure you take it. But again, we need to start, since the NNF are found, we talked about that founder experiment, we need to figure out how to do that. So when we get back and we start looking at ways you do that in the lab, one of it is called the law of the method of initial rates. And so we can actually figure out what the order of the reaction is by taking data and putting it into the rate law over and over again until we start to get those numbers to pop out. And then after that, if we were working with differential rate laws, what do you think comes next? What's the opposite of a differential? Integrated rate law. Miracles aren't hard, we're just being anti-derivative. They're not dumb.
Calculus is my favorite. I took like I took I feel like I took